let's talk about a current carrying element or a wire that's got current flowing towards the right. Now, current I is going to be positive charge flow. Okay, even though we know there really aren't positives moving in the wire, it's going to be considered positive charge flow. And we're going to try to picture a compass above and below the wire to help us picture what's going on here. Now, when we have a current going through the wire, and this is called Ampere's law, we're going to wind up with a magnetic field that forms around that wire in circles, in planes, perpendicular to that wire. It is not a spiral. There's our field lines going around like this. Okay, form circles and planes perpendicular to that wire. Now the first thing we need to do is we need to figure out how can we determine whether this is going around like this around the wire or going the other direction around that wire. And the way we do that is using a right-hand rule. We're going to take our hand and we're going to curl it kind of like we're hitchhiking. Okay? Our thumb indicates the direction of the current flow. And our fingers wrap around with our fingertips pointing in the direction that the magnetic field goes around the wire. A lot of times I'll take a pen and hold it in my hand with the tip of the pen pointing in the direction that the current's flowing. I'll take my fingers, I'll wrap around, and my fingertips aim in the direction that the magnetic field goes around the wire, which means it's coming out of the page above the wire and into the page below the wire, which is exactly what we drew here. So let's jot down what the right-hand rule is. For that right-hand rule, you're going to curl your hand like you're hitching. Your thumb is going to point in the direction of the current. And your fingers, or your fingertips if you prefer, aim in the direction that the magnetic field goes around that wire. Now, I can draw this differently. This magnetic field is coming out of the page above and into the page down below. So what I can do is I can put a field of dots above the wire, and those dots mean out of the page. And then down here, I can put in a field of X's, and X's mean into the page. Now let's go back to our compass. We've got one on the top, one on the bottom. The magnetic field, here's my current coming out. The magnetic field is coming out of the page above, going in below. Out of the page above, going in below, and it's going around in a circle in a plane perpendicular to the wire. That means above that wire, if I put a compass there, that compass is going to point out of the page. Down below, the magnetic field is going into the page, so that means your compass will point into the page. Now, as always, we want to know how strong this magnetic field is. And to do that, there is a relatively simple equation. And it kind of makes sense. The only things that are going to really affect how strong the magnetic field is how far away you are from the center of the wire and how much current's going through there. So, your magnetic field strength is going to be equal to mu0. That is the vacuum permeability. It's a constant. It's basically how easily a magnetic field will pass through a vacuum times the current divided by 2 pi r. And so I, we know, is going to be our current. R is a distance from the center of the wire. Mu0, 4 pi times 10 to the negative 7th Tesla meter per ampere. And that's the next thing. B is the magnetic field strength. And it's measured in a unit called Teslas. Yes, named after Nikola Tesla. Right now, try to determine what the direction of the magnetic field is at point X for each one of these questions. The direction first, and then try to determine what is the magnitude in Teslas of that magnetic field. You've got a wire with 5 amps here, 0.5 meters away, 3 amps, 0.6 meters away, and 0.4 amps and 0.2 meters away from the center of that wire. Give that a try. All right, let's take a look at these. For the very first one over here, once again, right-hand rule. This X means you've got a wire with current going into the page. So your thumb points down into the page, and your fingers wrap around in the direction that the magnetic field is going around the wire. So I'm going to get a clockwise circle going around like this, which at that point means we're going to have your magnetic field pointing towards the bottom of the page. Please stick to top, bottom, left, right, in, out, clockwise and counterclockwise for your answers. Up and down are confusing. Up can mean towards the top of the page or out of the page. Down could mean into the page or towards the bottom of the page. So please be very careful about that. For the next one, well, notice that this is going to be a real pain in the neck to kind of twist my body like that. Please feel free to take the piece of paper and rotate it. Now all of a sudden, it's very simple. My thumb points in this direction, direction of the current. Fingers wrap around in the direction of the magnetic field. At this point, my magnetic field is going into the page. So, I take care of that. And I know that at this point, it's going to be into the page. Now, my magnetic field, I didn't show all the work like I did there. There's not a lot of room there, so the answer is 1 times 10 to the negative 6 Teslas, but it's basically exactly the same thing we did here, just with different numbers. This next one, guys, well, thumb points in the direction of the current flow, fingers wrap around, and they're coming out of the page down below the wire. So at this point here, it is out of the page. Okay, if I wanted to, I could put a field of dots there. Just like over here, I could have put a field of X's. But that's out of the page. And the magnetic field strength, once again, just putting numbers into the same exact equation, it's going to be 4 times 10 to the negative 7th Teslas.